Today we're going to talk about projectiles that are being launched at an angle instead of being launched horizontally. All right, so what happens is we have an angle and a vector, a velocity vector right here, and this is the original velocity, and it's taken off in this direction. But gravity is going to pull it along and pull it down towards this curve, okay? So this original velocity right here is V sub, we're going to call that V sub O, the original velocity. Okay, this right here, this velocity right here is a horizontal component of that velocity. And from yesterday and the day before, we know that the horizontal velocity is always going to be the same because the horizontal acceleration is 0. So I'm going to write that a of x is still equal to 0 meters per second squared. And also, so I'm going to label this just v sub x. Technically over on this side, it's v sub x sub o, but it doesn't matter because that v sub x is always going to stay the same. This one right here is v sub y of o for original, right? This is the original velocity right here. So again, I've set up a coordinate axis right here and right here, okay? And so this is the positive, right here is where this is being launched, this ball or whatever you want to call it. I kind of try to draw it like a little ball, okay? And so it goes up and follows this parabolic path and comes back down and lands right here. And this is ground level right now, okay? All right, so we're shooting it from the ground, okay? If the ground level was down here, then these would be negative y's and these would be positive y's because this is my y-axis. And this is my x-axis, and there's nothing over here, so all of my x's are going to be positive. All right. So right at the top here, my initial velocity up here at the very top is still the vertical velocity is going to be 0. So right here at the top, we have that's why you're not seeing a vertical piece right here, okay? And you're seeing it here. So what's happening is as we go up, okay, the velocity was longer, right? It was, and that shows the magnitude of it. It's getting smaller as we go up, right? Until right here. And in this case right here, the velocity sub y, okay, so v sub y, the velocity at that y is equal to 0 meters per second. So right there, the velocity is 0 still, okay? So what happens is it has no vertical velocity, but it does have horizontal velocity, okay? And then as the projectile starts to come back down, now we're seeing the velocity going in the negative direction, okay? And it's starting to speed up, but we still have a horizontal component here, okay? And we wind up down here, we could break this velocity vector up into a horizontal component and a vertical component, all right? This right here, this horizontal distance from where you launch it to where it lands, that horizontal distance is called the range. Okay, like maybe you've seen like videos of people back when they were shooting rockets off at NASA. Well, I guess they are now, SpaceX and all that. But they said downrange, right? Downrange. This is the downrange part that they're talking about. Okay. Any point on here, okay, any point on here will have an x and a y coordinate. So the x coordinate is going to be the horizontal distance. And so that's going to be the horizontal distance it travels. And the y coordinate, it's not going to be displacement, okay, in this scenario. So this is the height of the projectile or position of the projectile. And I should say vertical position. And then this right here, this x right here, is the horizontal position. It's also going to be the horizontal distance it's traveled, okay? Okay. All right, so let's talk about how we can get the starting velocity, horizontal velocity, and the starting vertical velocity from this original velocity. All right. So here's the vector from above. This vector right here is right here, okay? So I've just kind of zoomed in on it. This is my V sub O, all right? And this is my velocity, horizontal velocity, V sub X. And this is gonna represent my vertical velocity original, okay? Okay, so right here, we're gonna transfer this, we're gonna translate this vector over here, and we're gonna make this right triangle. That's what we've been doing. So now this is V sub O, this is V sub Y comma O for original vertical velocity, and this is V sub X. And once again, I'm gonna keep saying this so you understand. There's a reason I'm not putting comma 0 here, or comma O, and that's because there's no acceleration. So this is not going to change. The V sub X is the same V sub X at any point in time. This horizontal velocity is always going to be the same. Okay. So what we can do is we can get this horizontal component from this original component using cosine theta. All right. So I know cosine theta is the adjacent leg, which is this, over the hypotenuse, which is V sub O. Okay. So cosine of angle theta is equal to V sub X over V sub O. And so what I can do is multiply both sides by the original velocity, and I'll have the horizontal velocity. So V sub X is going to be V sub O times cosine of theta. We can do very similar right here. We can do sine theta to get this one, okay? So sine theta is equal to the velocity in the y direction original over V sub O. And again, I can multiply both sides by the original velocity, and I get V sub y comma O equal to the original velocity, which is this green one, right? That's the direction of the velocity, okay? Times sine of theta. Okay, so now let's talk about projectiles launched horizontally, okay, and at an angle. These equations, okay, these equations were used to get these, all right? It's just some of these became 0 when it was launched horizontally, if you remember, okay? So right here, this V sub X, okay, we know now that when it's launched at an angle, this V sub X becomes V sub O times cosine of theta. So you could rewrite this if you wanted to as, I'm not going to do it this way, but I'm just telling you, you could. X, the horizontal position, is equal to V sub O cosine of angle theta times t, because this right here is my V sub X. Okay, so I can do that with all of these, all right, and they become equations that involve trig functions, all right? So this one comes from this because when it's launched horizontally, the original velocity, okay, for this one, V sub y comma 0 was equal to 0 meters per second. So that's why it's missing, this one is missing this little piece right here, okay, because that was 0. So what happens is this becomes V sub O sine theta. So this one we can convert to V sub y. And I'm using V sub y because this is going to be the velocity for at any time. It's equal to V sub O, the original velocity at that angle, sine of theta, plus the acceleration in the y direction times time. Okay, and so right here, same idea. Okay, this over here was 0, so that's why that's why this one, when it's launched horizontally, is missing this piece of the equation. So this one becomes y is equal to v sub o sine theta times t, that's my t right there, plus 1/2 a sub y times t squared. And then this one, I'm going to come down here so I have a little more room to write. V sub y, okay, the vertical velocity, okay, at any time squared is equal to, this one becomes v sub o sine of theta squared plus 2 times the acceleration in the y direction times y. And remember, a sub y, for all of these, a sub y is equal to g, which is negative 9.8 meters per second squared. All right. All right, we're ready to do some problems, because all it is going to be, I'm going to have to give you the angle. All right, let me zoom out a little bit. All I'm going to have to do is give you the angle and the initial velocity vector, okay? And then we can break it down into the horizontal and vertical components and just plug everything in, okay? So here's all the equations, all the motion, okay? This is the horizontal velocity. It can be, found by taking v sub o cosine theta, just like I showed you on the last page, okay? And then here's the same equations, right? So here we go. First example, projectile is fired with an initial speed of 75.2 meters per second at an angle of 34.5 degrees above the horizontal. So that's the angle made with the horizontal and this vector, okay? Above the horizontal on a long, flat firing range. Okay, so basically what it is here's my vector, right? Here's my 75.2 meters per second. All right, and I know the angle here is this 34.5 degrees. Okay, so here's going to be my horizontal velocity, and this one's going to be my vertical velocity. Okay, so this is my v, and the path of this, it's going to go like this, right? It's going to go up and then start to curve and then come back down. It's going to follow a parabolic path. This is going to be my positive x-axis. We're shooting it from the ground level and it's going to land on the ground, okay? So my axis would go right through here. Again, I want the origin because then x sub 0 and y sub 0 are both 0, and we don't have to worry about those in the formulas then, okay? So this is my v sub x, and this is my vertical velocity, my initial vertical velocity, v sub y o. Okay, so v sub x is going to equal 75.2 cosine of 34.5 degrees. So putting that into my calculator, okay, 75.2 cosine, make sure you're in degree mode, cosine of 34.5, and press enter, and you get 61.97. So on these intermediate steps, okay, I want you to go 2 decimal places, okay? So 61.97. This was meters per second, and when we do cosine, there's no units, so this is still meters per second. So that's the horizontal velocity, okay, starting, and it's going to be the velocity the entire time horizontally, okay? And then we have v sub y original, and that would be 75.2 meters per second, sine of 34.5 degrees. And then we're going to put that into our calculator. Okay, so 75.2 sine of 34.5. And we get 42.59. And that's meters per second. Okay, so now we know the vertical velocity and we know the starting we know the horizontal velocity, it's always going to be that. Okay, it doesn't matter what time it is, it's always going to be that. The vertical velocity, okay, remember, as it goes up, this is going to decrease and get slower and slower and slower until right here at the very top, v sub y is equal to 0 meters per second. And it's because of the acceleration that this is going to decrease, okay? So here's the first question, all right? Find the time it takes to reach its maximum height. So it's going to reach its maximum height right here when the velocity, the vertical velocity is 0, okay? So I'm going to use this equation right here, okay? Because I know v sub y is equal to 0 meters per second when it reaches this top, okay? Whenever this time is right here, the time it's going to take to reach a 0 velocity, we know our starting vertical velocity is 42.59. So v sub y comma o is equal to 42.59 meters per second. And I know my my acceleration in the y direction, that's negative 9.8 meters per second squared. And so all we need to do is figure out time and we'll have it, right? Okay, so we know that for using this equation, v sub y is equal to v sub y comma o plus a sub y times t, all right, is the equation that we're going to use. V sub y, that's 0 meters per second, is equal to v sub y o, which is 42.59 meters per second. I'm going to put parentheses around that, plus the negative 9.8 meters per second squared times time. Okay, now this 0, this is just 0. Okay, so I'm going to move this over and it becomes 9 point, because it's negative here, when I move it to the other side, it becomes positive. So 9.8 meters per second squared times time is equal to the 42.59 meters per second. And then I'm going to divide by the 9.8 and I will have t is equal to 42.59 meters per second divided by 9.8 meters per second squared. And that's going to give me a time. Sorry, you couldn't see it. Okay, so that's going to give me a time. I'm going to turn on my calculator and get the time here. So 42.59 divided by 9.8. And we get 4. So this is an intermediate, so I want you to write this as 4.35 seconds, okay? All right, so it's going to take 4.35 seconds for this projectile to reach its maximum height. I wish I had better writing, okay? It's maximum height. I wish I could write fast and prettier, okay? All right, next problem. I'm gonna zoom out a little bit so we can see this a little bit easier because I wanna refer back to this, okay? All right, so now what we wanna do is we wanna find the maximum height reached by the projectile. So we found the time it took. Okay, so now we got to find the how high it went. Okay, now y is my height. Okay, so right here, I'm going to use this equation because I know I'm trying to find my y. Okay, because that's the y. If I go back, okay, actually I can do it right here. This point right here, any point on here is going to be x comma y. X is the horizontal position and y is the vertical position. That's going to be maximum height right up here Well, that's all depending upon the time, right? And we just figured out that it took 4.35 seconds. So we're going to take the 4.35 seconds and put it in for our time here and our time here. And we already know the acceleration and we know our starting vertical velocity. So we can just go right to it, okay? So we know, all right, I'm going to do it in a different color. We're trying to find y, because that's my height, okay? And we know v sub y comma o is equal to, from up here, 42.59 meters per second. I also know my t. T is 4.35 seconds. I know a sub y, and a sub y is negative 9.8 meters per second squared. And I just realized you can't see it. Sorry, guys. Okay. So let me say it again. Okay. So we're going to find y, or we're trying to find y, because y is this vertical distance. And I want to find the y right here. Okay. And I know that's why I did this first problem, is we had to get the time in order to figure out this velocity. Okay. And then, so a sub y, the acceleration due to gravity, is negative 9.8 meters per second squared. Okay. And so we're ready to go. So we're going to use y is equal to v sub y comma o times time plus 1/2 a sub y t squared. So that makes y is equal to v sub y o, which is 42.59 meters per second, times t, which is 4.35 seconds, plus the 1/2 the acceleration due to gravity, which is negative 9.8 meters per second squared, times t, which is 4.35 seconds squared. Okay. So we're just going to put that straight into our calculator. Okay. So 42.59, actually I'm going to use parentheses. So 42.59, close the parentheses, 4.35 plus 1/2. So I'm going to get the fraction bar, 1/2, and then negative 9.8, and then and then another parenthesis and 4.35 and squared. And we get 92.55 meters. Okay. So, and I want to make sure that you understand the units here. Okay. It's a distance, right? So it's going to have to be like feet, meters. Okay. When we multiply these, the seconds cancel and you're left with meters here. Here you have the units are meters over second squareds, but you're squaring the seconds here. So that's second squareds. So your second squareds cancel and you're left with just the meters. Okay, so this is meters plus meters, and that's what we're going to get. Okay, so the maximum height reached by the projectile is 92.55 meters. All right. Let's go. There's another part to this. Let's turn the page. All right. So the next part of this is we want to find the total time the projectile was in the air. Okay. So we know, because it's a projectile, it's starting on the ground and going up and then coming back down and landing on the ground, right? And this was the maximum height. Remember, the time going up, equals the time coming down. Well, the time going up is the time it took to reach its maximum height. We know that's 4.35 seconds, right? So if time up equals time down, the total time the projectile was in the air it was 4.35 seconds going up, and it was also 4.35 seconds coming down. Okay, so the time would be 4.35 plus 4.35, or time 2 times 4.35, okay? So the total time projectile was in the air was, and we would just do 2 times 4.35 seconds, and 2 times 4.35 seconds would be 8.7 seconds. Okay, so it was in the air for 8.7 seconds. That's a long time, okay, to be in the air like that. Okay, so then the next thing, okay, so that means, okay, it took 8.7 seconds to go up and then come back down, right? Up and down. That was the same time it took to go the horizontal distance it traveled, okay? So here we go, find the total horizontal distance covered by the projectile. And this is called the range of the projectile, okay? So up here at the very top, we have V sub x, okay? We have this one, x, okay, is equal to V sub x, the velocity, times how long it was going at that velocity. Well, we know the original horizontal velocity was 61.97 seconds. And we went 61.97 seconds, 61.97 meters per second rather, for 8.7 seconds. So if we multiply this, we're going to get how far the projectile went horizontally. Okay, so we're going to use, because we know V sub x is equal to 61.97 meters per second. And I know the time it went horizontal was 8.7 seconds. Then I'm going to be able to find the position, which is also going to be the distance traveled horizontally. Okay, so I'm going to use x is equal to V sub x times time. So this x is equal to my horizontal velocity, which is 61.97 meters per second, times 8.7 seconds. And that would give you 61.97 times 8.7, and we get 539.14. So 539.14 meters. Okay, so the total horizontal distance covered by the projectile went that far horizontally. Okay, so the horizontal distance covered by the projectile was 539.14 meters. All right. Okay, so the last part of this, okay, let's do this next part. So the last part of this, the velocity of the projectile, I want to find the velocity of the projectile 1.50 seconds after firing it. Okay, so I need to know, okay, what the horizontal, okay, vector is, and the horizontal velocity is V sub x, and that was continually 61.97 meters per second, okay? And I need to figure out the velocity vector for the vertical piece after 1.5 seconds, okay? So I'm gonna need to use this equation right here, because this will give me the vertical velocity if I know the initial vertical velocity plus the acceleration times time. And I know my time is 1.50 seconds. Okay, so I'm going to use v sub y is equal to v sub yo plus a sub y times t. And I know v sub yo is equal to the 42.59 meters per second. I know a sub y is equal to negative 9.8 meters per second squared. And I know my time is 1.50 seconds. Okay, so v sub y, the vertical velocity, is 42.59 meters per second plus negative 9.8 meters per second squared times 1.50 seconds. And see, when I multiply these, that's going to give me seconds in the denominator here. Okay. All right. So we have 42.59 on our calculator, and then plus a negative 9.8, and then times 1.5. And we get 27.89. So that's the vertical velocity. Okay, so the vertical velocity is 27.89. And that's meters per second. Okay, so it's going horizontally 61.97 meters per second, and it's going vertically up 27.89 meters per second. So what that means is it's going to the right. Okay, and this would be the 61.97 meters per second. And at 1.5 seconds, it's still working its way up. And it's 27.89 meters per second. Okay, so what we have to do is we have to find the velocity vector for this, okay? So I'm drawing this up. If this turned out to be negative, I would actually be coming down, okay? So if the time was after 4.35 seconds, this velocity vector would actually be coming down this way, okay? So here's my vector, my velocity vector. I gotta find the magnitude of that, okay? So that is gonna be my V at 1.5 seconds. I'm gonna call this V sub R. All right, so we can get that by using Pythagorean theorem, okay? So V sub R is equal to the square root of 61.97 meters per second, and we're gonna square that. And I'm gonna add to that the 27.89 meters per second squared. And that gives me a resultant velocity vector of just making sure I type everything in right. 67.96 meters per second, okay? And then we have to give the direction angle, right? So the direction angle would be, we could use tan theta is equal to 27.89 meters per second over the leg, and I should say this, we're finding this angle right here, okay? So then 61.97 meters per second, because that's the adjacent leg. And all I would need to do is angle theta would equal tan inverse of 27.89 over 61.97. And so my angle theta is 24.22 degrees, 24.23 degrees. Okay. So So it's the velocity after 1.5 seconds is 67.96 meters per second at an angle of 27.23 degrees above the horizontal. Okay, so we would say 67.96 meters per second and then 24.23 degrees above the horizontal. Okay, and that's the velocity. Sorry, that's a little messy. Okay,